I guess you learned geometric series even in high school, right? Okay. Yeah. All right. So let's do a couple examples real quick. For example, this sequence, series, not sequence. I'm sorry. This is just the series, geometric series. Sum of 1 over 2 to the power n, right? N from 1 to infinity, minus 1. So this is just, r is just 1 over 2, and it is in absolute value less than 1, right? Therefore, this is just a over 1 minus r. A is just 1, so a is 1. So this is 1 minus 1 minus 1 over 2, so this is just 2. Okay, let me just also do this one. Pi minus e plus e squared over pi uh, minus e cubed over pi squared, and so on. This is just the series pi times minus e over pi n minus 1. You see, when n equals 1, you have zeroth power, which is just 1, so I have pi. When n equals 2, I have e over pi with a minus sign, so it is just minus e. When n equals 3, I have minus e over pi squared, so it is e squared over pi, and so on. So here, this is again a geometric series. A is just pi, and r is minus e over pi, and r in absolute value is of course e over pi. E is 2 point something, pi is 3 point something, so this is less than 1. Therefore, this is just a over again 1 minus r. So a is just pi minus 1 minus r. R is minus e over pi, sorry, minus e over pi. So this is just pi over, this is plus pi plus e squared. Yes. All right. Okay. Uh, there is another uh, telescoping series and harmonic series. Mhm. Okay. Telescoping series is the following. Is something similar to the following. Let me explain on an example. So show that the series below is convergent and find its sum. So let's do that. The series is this. N from 1 to infinity 1 over n times n plus 1. Okay. How can we do this? Well, solution. So this is just this series and from 1 to infinity an, where an is 1 over n times n plus 1. Okay. To check whether it is convergent or not, we have to form the sum of partial sums. The sequence of partial sums. The sequence of partial sums is what? Sn. And what is Sn? It is a1 plus a2 up to an. Okay. Now, what is this? This is just 1 times 2 and then 2 times 3 up to n times n plus 1. Alright. The idea is the following. Uh, Note that 1 over, okay, let me write it here, n times n plus 1 can be written like this. This is just 1 over n minus 1 over n plus 1, right? 1 over n times n plus 1 is the difference of 1 over n and minus 1 over n. 1 over n and 1 over n plus 1, sorry. So, for the first term, then I can write the following. This is just 1 over 1 minus 1 over 2. For the second term, I can write 1 over 2 minus 1 over 3. And then 1 over 3 minus 1 over 4. Up to where? 1 over n minus 1 over n plus 1. And then we observe the following. You see, here in each parenthesis, the second term is cancelled with the first term of the next parenthesis. So 1 over 2 is cancelled with this one. 1 over 3 is cancelled with this one. 1 over 4 is cancelled with this one. And it will go like this. And the last term that will be cancelled will be this one with the second term of the previous term. So what is left? Well, only two terms left, right? What are they? Here the first term is left, which is 1. And here the last term is left, which is 1 over n plus 1. So the sequence of nth partial sums is given by this, formula. Sn is equal to 1 minus n plus 1. So Sn is just this. Does this converges? Yes, right? Limit of this as n goes to infinity, Sn is what? This is limit as n goes to infinity, 1 minus 1 over n plus 1. 1 is the constant sequence. It has limit 1. 1 over n or n plus 1. As n goes to infinity, it will go to 0. So this series sequence is convergent and its limit is 1. Hence, the series from 1 to infinity 1 over n times n plus 1 is convergent and equals to 1. This sum converges to 1. Okay? This is why it is called a telescoping series. You have terms that cancels each other, right? Like a telescopic antenna, right? It has parts, and one part goes inside the other one, right? It gets smaller and smaller when you squeeze it. It is like this one, right? All the middle terms cancels, and you have only the first and last term left. Okay, so this is the telescoping series. What about the harmonic series? Series of this kind are called telescoping series. Uh, what about harmonic series? What is this? Harmonic series is the series uh, given like this. Sum of 1 over n from 1 to infinity. So this is the series 1 plus 1 over 2 plus 1 over 3 till infinity. Okay. What about this one? Well, is this convergent or divergent? Well, uh, we have to look at the sums of partial sums, sequence of partial sums, sequence of partial sums, Sn. What is this? 1 plus 1 over 2 up to 1 over n. And I wonder whether this limit exists or not. Here we use a geometric idea, namely the following. Uh, okay. All right. So here is the graph of the function y equals 1 over x. And here is, oh, sorry, 1, 2, 3, 4, 5, and so on. Let's say here I have n, uh, n plus 1. Okay. And then here you see, I can form these rectangles like this. Sorry. And so on. And here I will have this rectangle. Uh, what is the area of this rectangles? The area of this one, this rectangle is, so this point is 1, therefore this should be 1. This is not a correct picture. 1 is over here, but here it is just something even smaller, but doesn't doesn't matter. The area of this rectangle, right? The area of this rectangle is 1 unit because the base length is 1, height is 1. Why is that? Because this is the curve 1 over x. So when x equals 1, y coordinate is 1. What about the area of this rectangle? It is, this thing is just 1 over 2. So the height is 1 over 2. Base length is 1. Therefore, the area of this rectangle is 1 over 2. What about the area of this one? 1 over 3. And the area of this one will be 1 over n, right? So Sn, which is just 1 plus 1 over 2 up to 1 over n, is the sum of areas of the rectangles. Burada anlaştık mı? Bu dikdörtgenlerin alanlarının toplamı şeye eşit. Bu toplama eşit. First rectangle has area 1 and then 1 over 2, 1 over 3, 1 over 4 and so on. Well, that area is larger than this area, right? Consider the area under the curve. Right? This area is strictly less than the area of the sum of the rectangles. Note that Sn is larger than the area under the curve y equals 1 over x, right? From x equals 1 to x equals n plus 1. Değil mi? Birden n artı 1'e kadar ki bölümde y eşittir 1 bölü x eğrisinin altında kalan alan dikdörtgenlerin alanlarının toplamından küçük. Well, we have a name for this area under the curve, right? What is that? It is the integral, right? Hence, whatever this Sn is, it is larger than the area under the curve, which is the integral from x equals 1 up to n plus 1 of 1 over x dx. And we know what this is, right? So Sn, whatever it is less than, greater than ln x, 1 and n plus 1. So this is just ln n plus 1 minus ln 1, which is just 0. So this is ln n plus 1. So Sn is larger than ln n plus 1. But logarithm of n plus 1 is, is not bounded, right? As n goes to infinity, logarithm n goes to infinity. It grows very slowly, but it goes to infinity. Since limit as n goes to infinity, ln x or x goes to infinity is infinite, we see that this limit is infinite. Okay, so it is not convergent. Hence, Sn, and thus this is the sequence of partial sums of the series. So 1 over n is divergent. Okay, but let me remark the following. So if you add 1 over n's, that sum will grow and it will go to infinity. However, if you plug this formula into a computer and let the computers, compute this sum for large values of n, you will never see big numbers, okay? Because it grows similar to ln n, or any logarithm. And you see, if you have 10 to the power, let's say 1000, it is just this. But this number is so big, 10 to the power 1000, okay, is so big. Actually, some people computed that if you let a computer run at the time of Big Bang till now, and if the computer, let's say, is 1 million times stronger than the computers we have today, the sum it would compute would be like 70 or 80. Okay, so it is that small. But again, I mean, this sum is infinite. However, if you just try to compute it by hand and see that it goes to infinity, you will probably never see that. Okay, because it grows very slowly. It, it grows logarithmically and it's very slow. Yani bu serinin toplamı sonsuz ama hani toplayayım da sonsuza gittiğini göreyim derseniz hiç göremeyeceksiniz büyük ihtimalle. Tamam mı? O yüzden de hani bir ispat yapmanız lazım burada. Hani böyle deneyerek falan olacak bir şey değil bu. Okay. Now, some theorems about series. We will use these theorems to determine whether a given series is convergent or not, and find its value if possible. Sometimes it is easy to find the sum of the series, but sometimes it is not easy. If a series AN converges, then the sequence convergence is convergent, AN is convergent, and its limit is 0. Okay, therefore, if AN is not convergent to 0, okay, then the series is divergent. So for a series to be convergent, one must have the limit of an equals 0. Okay, so if the limit of an doesn't exist, or if it exists but not equal to 0, then there is no way this series will be convergent. Okay, and that's called the n-term test. This theorem is also known as the nth term test for convergence of series. And proof is very easy. Proof is very easy. We will do easy proofs. We will skip the difficult ones. So what do we mean by a series is convergent? Well, you have to look at its sequence of partial sums. So Sn. What was Sn? Sn is the nth partial sum, the sum of the first n terms. And what is the statement? We assume that this is convergent. Then we have to show that An is convergent to 0? Well, by assumption, limit Sn, let's say equals L exists, right? This limit exists. But then, what is the limit of Sn plus 1? If a sequence goes to L, if you shift the sequence 1 unit, then it will converge again L, right? Yani siz nereye gidiyorsanız sizin tam bir adım önünüzde olan kişi o da oraya gidiyordur. Veya tersine, değil mi? Siz birisini bir adım geriden takip ediyorsanız o nereye gidiyorsa siz de oraya gidersiniz. So this is exactly the same thing. If someone goes somewhere and if you are just one step behind that person, then you will go to the same place. Okay? Tabii that's not one, that's L. But now, what is AN? AN is this. AN is just SN, right? The sum of first n terms minus Sn minus 1. The sum of first and minus first terms, right? So that limit of an will be what? Limit of Sn minus 1. Bunu şöyle yapayım. Bu S şey olsun. N minus 1. But this is convergent and this is convergent, both of them, and they have the same limit. So the difference is convergent. This is limit of Sn minus limit of Sn minus 1. So this is just L minus L, which is 0. And that proves the theorem. Tamam mı? Bakın bunun ne kadar kuvvetli olduğunu göreceksiniz. Now we see how strong this result is in practice. Daha yukarı mı gideyim? Ha, tabii ki tabii. Evet evet hepsi. Hı. Okay. Okay, 7. Okay, let's look at, for example, this one. So, okay. N divided by 2n minus 1. So, we consider this series n over 2n minus 1, and from 1 to infinity. Here, an is just n over 2n minus 1. And we see right away that this is convergent, but the limit is not 0, right? Note that limit an as n goes to infinity, n over 2n minus 1, right, is just n over 2n minus 1. I can divide both numerator and denominator by n, so I get this 2 minus 1 over n, right? And then the numerator is constant, so it goes to 1. This goes to 2 and 1 over n goes to 0 as n goes to infinity. So this limit is 1 over 2. The limit of an exists, but it is not 0. So this is not 0. Hence, by the previous theorem, which is called the n-term test, hence uh, by the n-term test, the series, which series? This series, n over 2n minus 1 is divergent. Divergent. Okay, so that's a very practical test. Another one. Uh, Again, n from 1 to infinity minus 1 to the power n times sine 1 over n. Is this convergent or not? Okay. Well, here an is what? It is minus 1 to the power n times sine 1 over n. Okay, now what happens as n goes to infinity? Well, let's check. So I wonder whether this sum is convergent or not. If I add these numbers, will I get, you know, sum a real number, or it will be divergent? An. Actually, let's look at its absolute value. So it is minus 1 to the power n, n times sine 1 over n. So this is just limit n times sine 1 over n. You may object why, this is positive, right? Absolute value of something should be positive. This thing is positive because 1 over n is very small as n goes to infinity. And if x is a small positive number, very close to 0, then sign of that number is positive. Therefore, absolute value of this expression for big N values is equal to this gadget. What about this limit? Well, I don't know this limit, but we can compute the following. As x goes to infinity, x over sine 1 over x. How? I can write it this way. This is sine 1 over x divided by 1 over x. So this is, as n goes to infinity, this is 0. Sine 1 over x goes to 0. Sine 0 is 0. So this is a 0 over 0 case. And for that, we have L'Hopital's rule, right? Both functions are differentiable. So I can use L'Hopital's rule. And this is just, so sine 1 over x derivative 1 over x derivative. What about this? Derivative of this, well, derivative of the denominator is just minus 1 over x squared. And this is just cosine 1 over x times derivative of the inside, which is minus 1 over x squared. So 1 over x squareds are cancelled. So this is just cosine 1 over x. Sorry. As x goes to infinity, 1 over x goes to 0. And cosine is a continuous function. If the argument inside cosine goes to 0, cosine of that argument will go to cosine 0. So this limit is just cosine 0, which is just 1. So limit of this expression, limit of absolute value of a n, turned out to be, okay, now this is 1, hence limit as n goes to infinity n times sine 1 over n, which is equal to limit as x goes to infinity, this. This limit exists, therefore these two are the same. So this is just 1, and hence, and thus limit of a n is equal to 1, so that this limit cannot be 0, right? If a n had limit 0, then its absolute value would have the same limit. But absolute value has limit 1. Therefore, this limit cannot be 0. This means this therefore the series an, which is just minus 1 to the power n times sine 1 over n, is divergent by the nth term test. Okay, let's say break. After the break, I'll continue.